You can feel its intense heat, smell its smoke, and hear the satisfying crackle of the logs. It engages so many of our senses at once that our brains instinctively process it as a physical thing. But if you look closely at a flame, what exactly are you looking at? It's obviously not a solid, and it's clearly not a liquid. Because it mingles with the air, you might guess it's a gas, but gases can sit in a container indefinitely, whereas a fire always eventually burns out. One might proudly proclaim that fire is a plasma, the fourth state of matter where atoms are stripped of their electrons. But there's a problem with that too. Plasmas require electric fields or extreme temperatures of tens of thousands of degrees to exist, while a normal flame is only a few hundred degrees, falling way below the threshold of a plasma. So if a fire isn't a solid, a liquid, a gas, or a plasma, what state of matter is it? To understand what fire actually is, we have to stop thinking of it as a physical object and start thinking of it as an event. Fire is our sensory experience of a chemical reaction called combustion. Think about the leaves changing color in the fall, the sweet smell of fruit as it ripens, or the glowing blink of a firefly in the dark. All of these are sensory clues that a chemical reaction is taking place. Fire just happens to engage almost all of our senses at the exact same time, creating such a vivid, intense experience that we expect it to be a tangible thing. But the twisting flame you see is simply the visible, glowing region of a gas where an exothermic chain reaction is happening. This reaction requires three fundamental things to sustain itself: fuel, oxygen, and heat. The oxygen in the air and the carbon and hydrogen inside a piece of wood or a candle don't do anything on their own. They need a little outside heat to get things started. But solid fuel doesn't actually burn. When a log or a candle is heated to its ignition temperature, the solid material is vaporized and ripped into smaller chunks. In a campfire, the heat causes the walls of the wood cells to decompose, releasing sugars and other molecules into the air. In a candle, the heat melts and vaporizes the wax. This crucial process is called pyrolysis, and you cannot have a flame without it. If you look closely at a candle, you can actually see a dark cone right around the wick where there is no fire. That is just a pocket of vaporized wax coming off the candle that hasn't started to burn yet. Because the reaction can only happen exactly where this vaporized fuel meets the oxygen in the air, candle flames are actually hollow inside. Once the vaporized hydrocarbons and hot oxygen slam into each other, their atoms begin to rearrange. Surprisingly, it isn't the molecular ripping apart that makes a fire hot. The formation of new molecules and new chemical bonds is what actually creates the heat. This newly generated heat drives the chain reaction forward, sustaining the fire by vaporizing more fuel, slamming more molecules into one another, and keeping the fuel at or above its ignition temperature. As this violent process unfolds in a wood fire, any trapped water inside the logs rapidly vaporizes, expands, and ruptures the wood around it, escaping with that satisfying campfire crackle. While chemistry tells us the recipe for this combustion, the spectacular light show we see is entirely physics. The dazzling colors of a flame are the result of two very different physical processes. When a flame burns incredibly cleanly, like the blue flame of a gas stove, a blowtorch, or the very bottom base of a candle flame, the heat excites the molecules. The electrons in those atoms get bumped into an excited state, and when they drop back down to their normal state, they give off a photon of light. This is quantum mechanics in action, emitting a characteristic pale blue light through atomic transitions. However, in a wood fire, a coal fire, or the upper sections of a candle flame, the fuel isn't pure and doesn't entirely burn. Not all the carbon gets converted into carbon dioxide. Instead, these leftover, unreacted carbon atoms clump together to form tiny particles of soot. These soot particles rise into the flames and heat up, bringing us to the second physical process, thermodynamics. Through a process called black body radiation, All objects glow with a color that depends entirely on their temperature. You and I don't glow with visible light because we are too cool. We glow in the infrared spectrum. But the soot inside a fire gets hot enough to glow with that familiar yellow, orange, and red light, much like the hot coals under a grill. That glowing hot soot is where almost all of a campfire or candle's light comes from. Eventually, at the very tip of the flame, all the soot burns away, leaving only invisible carbon dioxide and water vapor to float off into the air. You can even prove this anatomy of a flame yourself with a cold piece of metal. If you hold it near the wick, you'll recover unburned wax. In the yellow metal, you'll collect black soot. And at the very top, you'll catch condensation from the water vapor. The presence of different substances can also dramatically change the color of the light show. If you introduce elements like copper, calcium chloride, or potassium chloride into the mix, they add their own characteristic quantum hues to the flames, shifting the colors to vibrant greens, pinks, and purples. But no matter the color, the hottest flames will generally be white or blue, while cooler flames burn red and orange. Yet, perhaps the most recognizable feature of the fire is its shape. Those twisting, mesmerizing tongues snaking skyward. That iconic taper is entirely the work of gravity. Earth's gravitational pull causes cooler, denser air to sink down, which forces the hot, less dense carbon dioxide and water vapor created by combustion to expand and rise in a thinning column. This convection and buoyancy literally stretch the flame upward. If you were to light a match in a zero-gravity environment, like aboard the International Space Station, the flame would look completely different. Without gravity to pull dense air down and push hot air up, the molecules don't separate by density. The flame has nothing to tell it which way to go, so it spreads outward in all directions, looking like a perfectly round, glowing blue balloon. Eventually, even the hottest, most violent fires will run out of either fuel or oxygen. The chain reaction breaks, the temperatures drop, and those twisting flames give a final hiss, disappearing with a wisp of smoke as if they were never there at all. Our species has been gathering around this fleeting phenomenon for thousands of years, sitting together, asking questions, and telling stories over a flickering flame is largely what helped make us human in the first place. So the next time you strike a match or sit by a fire, remember that you aren't just looking at burning matter. You are watching a hollow, gravity-sculpted, self-sustaining chemical reaction, beautifully illuminated by the glowing laws of quantum mechanics and thermodynamics.